Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 7, Lesson 4 on similar figures. So for the remainder of Unit 7, we're really going to be talking about these things called similar figures, and we've really already kind of seen them, both probably in middle school mathematics and with what we've been doing with dilations. So let's get right into them and start talking about these things. Similar figures. We have now seen that when a shape is mapped with a dilation, it produces another shape that has side lengths that are scaled by the same factor and angle measurements that are the same as those of the pre-image. These figures have the same shape but different sizes, and we call them similar figures, right? So that's all it is, right? And let's kind of get into that technical definition right up here. Similar figures. Two geometric figures are called similar, shown by that little mark. That's actually called a tilde. If all pairs of corresponding sides are proportional, in other words, they've been scaled by the same factor, and all corresponding pairs of angles have equal measures. All right, so very, very important, right? This idea that two figures are similar if, right, when we take each set of corresponding sides and we divide them, we get the same number, and that division will produce the scaling factor, right? And then all the angles have the same size. So let's look at that in exercise number 1. In the diagram shown, triangle ABC is similar to triangle DEF. Letter A, use tracing paper to verify that all corresponding angle pairs are congruent. All right, well, we've done this before, but let's do it again. What I'd like you to do is pause the video and trace out triangle ABC on a piece of tracing paper, and then literally move it around on triangle DEF to just verify that all the angles of triangle DEF are equal to all the angles of triangle ABC. All right, well, it doesn't hurt to start with angle A, right? If I move angle A down there, I can see that those two angles are certainly congruent. If I move angle B up so that it corresponds with vertex E, I can see that those two angles are equal. And if I move C down to F, I can see that those two angles are equal. Move my little tracing paper off so that we can then move on to letter B. Talking about letter B, determine the lengths of the missing sides of both triangles. Show or explain how you found your answers. All right, so let's talk about EF. All right, let's find the missing side of EF. Now, the whole idea of sides being proportional to one another is the following, right? DE is the scaled version of AB. So if I take DE and I divide it by AB, that's got to be the same as if I take EF and I divide it by BC. All right? So those two have to be true. DE divided by AB has to be the same as EF divided by BC. Now, what is DE divided by AE? Well, DE is 14, AB is 7, and really, what does that tell us? It tells us that DE is twice the size of AB, right? They're all just equal to 2. So I can say that EF, which is what I'm looking for, divided by 8 is equal to 2, which of course then means that EF is 16. All right, and that's a piece of cake. Right? This triangle simply has side lengths that are twice the size of this triangle. Now, because the scaling factor is so easy, right, we can turn that around and we can say, well, all the lengths on this triangle are 1/2 of the lengths on this triangle, and therefore AC obviously has to be equal to 10. Okay? And again, the idea is very, very important. When we say that the corresponding sides of similar triangles are proportional, it means if I take one side from this triangle and I divide it by the corresponding side of that triangle, I'll get the same thing as if I take another side of this triangle and divide it by the corresponding side of that triangle, etc., right? That division results in the scaling constant that it would take to dilate one of those triangles and make it congruent to the other one. Speaking of which, let's take a look at letter C. Give a dilation of triangle ABC that would produce an image, triangle A prime, B prime, C prime, that is congruent to triangle DEF. How do you know it's congruent? Well, this is simple enough, right? So all I would need to do is dilate triangle ABC with a scale constant of 2. Now, for all dilations, there's really two things that are important: the scaling constant and the center of dilation. But in this case, the center of dilation is somewhat irrelevant, right? It could actually be here, it could be point B, it could be point A, it could be the moon. And it doesn't matter, right? Because no matter where the center of dilation is, if I dilate triangle ABC with a scale factor of 2, its side lengths are going to become 14, 20, and 16, right? So I'm going to say dilate triangle ABC using any center point and a scale factor equal to 2. Lots of red coming out there. And a scale factor equal to 2. All right. Now, how would we know, right, that the two triangles were congruent? Well, at this point, right, triangle A prime, B prime, C prime would have to be congruent to triangle DEF by the side congruence theorem, right? This thing would suddenly have side lengths of 14, 20, or its image, sorry, would have side lengths of 14, 20, and 16. And we know that two triangles that have three pairs of congruent sides between them, or all three corresponding pairs of sides are congruent by the side congruence theorem. All right. Similar figures. Now, we can define similar figures using dilations. We can now formally define two similar figures in a manner that's similar to how we defined two figures that were congruent. Remember, right? When we defined congruent figures, we said two figures will be congruent if a rigid motion, right, or a sequence of rigid motions would map one of the figures on top of the other figure. We can now define similar figures in a very, very similar way. Let's take a look. Similarity transformations. Two geometric figures are similar if there exists a similarity transformation that will map one figure onto the other. This transformation is either a dilation along with a sequence containing a dilation in combination with one or more rigid motions. Sorry, it should say a dilation alone or a sequence containing a dilation in combination with one or more rigid motions. So not along, but alone. Sorry about that. Now, again, make sure that you understand this. So sometimes we can literally just dilate one of those things, one figure, and it'll map right on top of the other figure. We don't have to do anything else. Just dilate this thing, and it'll map right on top of this one. Or possibly, we have to both dilate and do a translation along with maybe a reflection or a rotation or something like that. Of course, we can always throw those rigid motions in there because the rigid motions aren't going to change the size or the shape of the object. So let's take a look at exercise number 2. In the diagram below, triangle ABC is similar to triangle DEF. Describe a similarity transformation that will map triangle ABC onto triangle DEF. Be as specific as possible. Use tracing paper to help you visualize. All right, so I literally want to map triangle ABC so that it lies on top of triangle DEF, okay, using a similarity transformation. Now, there would be no way to do it with a dilation alone. There just wouldn't be. The thing isn't oriented right, it just wouldn't work out correct, okay? But using some other things, we can definitely get this thing to map on top of that. Now, just like when we had sequences of rigid motions, right, this is not going to be unique. In fact, there would be an infinite number of correct answers. So let's take a look at one, all right? Now, one thing that I think I'm going to do, notice that angle A and angle D have the same measure. So I think that the first thing I'd like to do is translate ABC so that point A maps to point D. So that's going to be my first thing. I'm going to translate triangle ABC so that A maps to D, right? And that's exactly what I did just right there. Now, what I really kind of want is I really want now this, which is, you know, A prime, B prime, whoops, B prime, C prime. I really now want A prime, B prime to lie right along DE, right? So now what I'd like to do is I'd like to rotate this triangle using D as the center so that A prime, D prime, or really A double prime, B double prime lands on DE. All right, I want to do something that looks like this. All right, so I'm going to rotate triangle A prime, B prime, C prime so that A prime, B prime maps onto DE, right? And now we get that picture that we're used to, right? That triangle that's sort of embedded within another triangle with this side length being parallel to that side length. Now I can finally do my dilation. Now, where do I want my center of dilation? Always at that shared angle, right? What do I want my constant of dilation to be? Well, that can be the ratio of any two corresponding side lengths, right? So right at this point, right, this is now A prime, double prime, and this is now B double prime and C double prime. So the last thing I'm going to do is I'm going to dilate triangle A double prime, B double prime, C double prime with a center at D and a scale constant, and we'll just bring this up a little bit, equal to literally the ratio of any one of the image lengths divided by its corresponding, its corresponding pre-image length. And I think I'll just take the image length DE divided by, right, A prime, A double prime, B double prime, but that's just divided by AB. And again, that scale constant could be DE divided by AB, it could be EF divided by BC, it could be DF divided by AC. Any of those are perfectly good. Now again, this isn't the only way to do it. We could have mapped it so that B went to E, and then I rotated it down so that BC was lying along EF. Or I could have mapped C to F and then rotated it up so that C was pegged here and CA then was somewhere along that. In every case, I would get something that sort of looks like this, a triangle embedded within a larger triangle. Okay, but that's the way we now define similar figures. If we can find a similarity transformation, which is either a dilation alone or a dilation with some rigid motions thrown in, that maps one figure on top of another figure, then we've got ourselves two similar figures. Okay, let's keep going. Exercise number 3. In the diagram shown, it is known that segment AM and segment BN intersect at point C such that triangle ABC is similar to triangle MNC. Give a similarity transformation that would map triangle ABC onto triangle MNC. Use tracing paper to help visualize. All right, so I would suggest now pause the video and see if you can do what we just did. I will say this one should be a little bit easier than the last one. Play around with it and see if you can come up with this dilation or this similarity transformation? All right, well notice, right, angle A is congruent to angle M and angle B is congruent to angle N. What I really kind of want is that embedded sort of situation. So what I'm going to do is the first thing I'm going to do is I'm going to take triangle ABC and I'm going to rotate it by 180 degrees around point C, right? Which is going to make it end up looking like that. So that's the first thing I'm going to do. I'm going to rotate triangle ABC by 180 degrees, so there's a rigid motion, about point C. All right. And of course then what we end up getting is that picture that we've gotten quite a few times already, that triangle embedded within another triangle. And at that point I'm ready to dilate, right? I am, right? And I'm going to have a center at C. And a scaling factor, again, can be any one of these corresponding lengths. Now, keep in mind, right now, here is my A prime, and here is my B prime, right? So let's now dilate. Let's see, that would be A prime, triangle A prime, B prime. And I can either call it C or C prime. I'll call it C prime. Dilate triangle A prime, B prime, C prime, using a center at C and a scale factor equal to, well, what do I want to do? I kind of like MN, this one, divided by, oh shoot, that's not where B prime is. B prime is down here and A prime is down there. My apologies for that. Those are just M and N, right? So I can now do the scaling factor, which takes my new length, right? The length I want, my image length, MN, and dividing it by its corresponding pre-image length, which is AB. All right? We could also do CM divided by CA, or Cn divided by Cb. Again, keeping in mind that the smaller triangle here now is our image triangle and the larger triangle is our pre-image. Always image divided by pre-image. Image divided by pre-image. Really critical. All right, let's go to the coordinate plane, right? Here we can start to assign numbers and all sorts of stuff like that. Exercise number 4. Given that triangle ABC is similar to triangle DEF on the grid shown, letter A, what scale factor would be needed to dilate triangle ABC so that its image is congruent to triangle DEF? Justify. All right, we'll see if you can figure out what the actual scale constant is. So this time you can give me a number, right? Probably a fraction, but it's going to be a number that if we dilated that particular triangle, it would then be congruent to that particular triangle. Pause the video now and see if you can figure out what that particular scale constant is. All right, well, what's really easy is just to take two lengths, one from the image and one from the pre-image, that are easy to figure out and that correspond to each other, and divide the two. And I think the easiest thing is to have K be equal to DE divided by AB, right? So these two particular lengths, here and here, correspond to each other. DE has a length of 6, AB has a length of 4, and that will reduce down to 3/2, or if you like decimals, 1.5. Right? And again, it makes sense that the scaling constant is larger than 1 because we're trying to dilate a smaller triangle to create a larger triangle. You would get exactly the same thing if you divided EF, the length of EF, by the length of BC, all right? And trickier, you would get the same thing if you divided the length of DF by the length of AC. But those two lengths would be harder to figure out because we would either have to use the Pythagorean theorem to come up with their lengths or the distance formula. All right. Let's take a look at letter B. Give a similarity transformation that would map triangle ABC onto triangle DEF, parentheses, multiple correct sequences. And I probably should have put that multiple correct sequences in on everything else we've done so far because there are multiple correct sequences. Let me get rid of this so that we can see it better. Why don't you pause the video now and go ahead and see if you can come up with a sequence. And again, there are many of them, so whatever one I come up with most likely won't be identical to the one you do. All right, well, the way I like to think about this one is I really need this right angle to kind of overlap that right angle. So personally, the first thing I would do is I would use a translation to map point B to point E. And we could actually give that exact translation, or we could just say, you know, translate triangle ABC so that point B maps to point E. All right, awesome. Now what I want is I kind of want that embedded triangle thing going on again. So what I'd like to do is I'd like to take this new triangle, which is really A prime, B prime, C prime, and I want to flip it, right? What do I want to flip it across? I want to reflect it across EF, right? So that's going to be my second thing. I'm going to just do this. I'm going to reflect triangle A prime, B prime, C prime across EF. All right, let me do that real quick. Let me flip it left, right, and maybe adjust a little bit, and there it is, right? And now, yet again, we've got that triangle embedded within another triangle. So the last thing I want to do is I want to dilate this thing with a center at point E and a scale constant of 3/2. So now I will dilate, and at this point it would be triangle A prime prime, B prime prime, C prime prime with a center at E and a scale constant equal to 1.5. Now, it's harder for me to show you that, especially the actual scaling, but I can literally get this thing to scale up. I just can't get I can't particularly get the center to stay at E. That's a limitation of this software. But when I do stretch a particular image or shrink a particular image in this software, it is most certainly dilating it. All right? It's just using some mathematics that we can't see because it's in the programming. All right, let me kind of move this out of the way and let me bring this thing up. Pause the video now. I still have this in the way. Pause the video now and write down any of that you might need to. All right, let's look at one last problem. A common scenario that gives rise to similar triangles is when a line segment is drawn within a triangle that is parallel to one of its sides, okay? And we've already seen this once, but let's take a look at it again. Exercise number 5. In the diagram shown, points B, C, and D lie on AC and AE, such that BD is parallel to CE. Give a dilation that would map triangle ABD onto triangle ACE. Explain. All right, well, why don't you go ahead and do that? All right, so this is the picture that we just keep seeing, right? We keep seeing this picture again and again and again. So it's pretty simple, right? We're going to want our center of dilation at A. So we want to have our center at A, all right? And we can have a scaling constant that is quite a few different things, right? One choice of the scaling constant, because now keep in mind, we want to map ABD, the smaller one, onto ACE, the larger one, right? Then we could either do CE divided by BE, we could do AC divided by AB, or we could do AE divided by AD, right? And I think I'm gonna write those out. Center at A with any of the following scaling constants. So it could be k equals CE divided by BD, or AC divided by AB, or AE divided by AD. All right, right? Any of those would work and get the job done, as we've been seeing all along, right? And again, it kind of makes sense because these lines are parallel. These two angles have to be congruent. These two angles have to be congruent. Obviously, this angle is congruent to itself. So as soon as I've stretched all the lengths of this triangle out so that they're the lengths of this triangle, the larger one, all the angles are going to remain the same. So I'm going to have these two triangles that have all the same lengths, right, and all the same angles. Therefore, mapping one triangle on top of the other one. Now, let's take a look at letter B. Circle the proportion that is incorrect based on the fact that triangle ABD is similar to triangle ACE. All right, now this is really critical. Problems like this come up on multiple choice all the time on state exams, and they can be very, very confusing, especially the ones that include the angles. So let's kind of take a look at them. In choice, the first choice, choice I guess, they say AC is divided by AB is equal to CE divided by BD. Now notice in this case, right, we're taking a large triangle and we're dividing it by the length on a small triangle, and it's the corresponding length, right? AC divided by AB, right, is equal to CE divided by BD. And again, that's large divided by small. Okay, and that's correct. All right, in similar triangles, corresponding sides are proportional, meaning that the ratios of the sides are equal to each other. Now let's take a look at one that has to do with angles. All right, now don't forget, and this is really critical, right? When you dilate a triangle or any figure, the angles don't change. So in this one it says the measure of angle A divided by the measure of angle ABD. Let me circle that. The measure of angle A divided by the measure of angle ABD, that's this, right, is equal to the measure of angle A divided by the measure of angle ACE. Well, yeah, sure, right? And the reason that this one's going to be true is that that angle and that angle have the same measure. That angle and that angle have the same measure. So if I do that one divided by that one, I better get the same as that one divided by that one, because literally it will be the same division problem. It's not even that like, oh, they both reduce down to 3/2. Literally, if angle A, right, is let's say equal to 60 degrees and angle B is equal to 45, this one's also equal to 45, okay, because they are similar triangles. Let's take a look back then at one that involves side lengths again, right? So in number 3, right, we've got AD divided by AE, so AD divided by AE, okay, in that case that's small divided by large, all right, is equal to AC. Let me put this one in red just so that it's easier, is equal to AC divided by AB. That one's not correct, right? The order's got to stay the same. So if I'm going to do small divided by large, which let's say is pre-image divided by image, then I still have to do small divided by large. I cannot switch the order. I can't go this divided by this is equal to this divided by this. It's got to be, okay, this triangle length divided by this triangle length is equal to this triangle length divided by this one. So if these two had been flipped just on the right-hand side, then it would have been okay. But this one is the one that's incorrect. All right, and we won't even check the last one. It would end up being correct. And for the same reason as number 2. Literally, it's the same angles divided by each other. Okay, So let's wrap this up, right? Today we finally introduced the thrust of the rest of the unit, which are what are called similar figures, all right? And we decided that what similar figures were simply the result of what you get when you take a figure and you dilate it. What you get is another figure that's similar to the original. And what is true about two figures that are similar? Well, one thing, all the angles in one figure will equal the corresponding angles in the other figure. That guarantees that the two figures have the same shape, right? The other piece is that corresponding sides between the two figures will be proportional. Now that's just a fancy way of saying if one side in one triangle is twice the corresponding side in the other one, all the sides have to be twice the corresponding length. And of course, a scaling factor of 2 is a rather nice scaling factor, but that's got to always be true. So if I take an image length and I divide it by a pre-image length, that number that I get, that ratio, has to stay consistent amongst all of the corresponding side pairs. Okay. We also looked at how you can justify that two triangles are similar by finding a similarity transformation, which either includes a dilation all by itself or a combination of a dilation along with one or more rigid motions. All right, we're going to work a ton more with similar figures as we go through this unit. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler. Until I see you again, keep thinking and keep solving problems.